your presentation.
Okay, sure. Yes. Before starting, like I have a couple of things about this. So you have mentioned that they are looking for metal forming and cutting operations, right? And rolling operations. Is it right, or is there any other requirement that you would like to specify something?
Bagaimana Pak Damora?
Ya, bisa Pak.
Yes, yes, please, Mr. Sivasai.
The same thing. Okay, sure.
Yeah.
Okay, fine. So I'll go through the presentation of our SIMUFACT forming, and which covers the details about what you're looking for, what it is capabilities, and then we'll go through some case studies based upon your queries that you are coming up.
Okay, good. Please.
Okay, sure. I'm just sharing the screen. Just let me know if it is visible or not. Okay, let's start the process. You can see the presentation, right?
Yes,
Yes.
I can see your share screen.
Okay, sure. So you are seeing the presenting view, or you are seeing the proper presentation view?
Yes.
Okay, sure. Thank you. So now today, yes. So now today I just take you through the SIMUFACT forming product lines and also some other case studies which SIMUFACT can do. Okay. Just before that, like what SIMUFACT is. So SIMUFACT is generally a metal manufacturing analysis software. So where is it origin? So it, the acronym SIMUFACT means simulating manufacturing process, and it is currently a manufacturing division of MSc. So any type of metal-based manufacturing process can be simulated in SIMUFACT. Okay, and in the SIMUFACT there are three different verticals like SIMUFACT forming, welding, and additive. So it can simulate different types of manufacturing methods. The SIMUFACT forming is what we'll be discussing today. Just before this, I just want to say, like, is my speed okay, or should I reduce my speed? Speed of talking. Hello.
Yes, we can see your share screen.
No, I know you can see the screen, but I am asking, is my voice okay, or should I make it slow, or am I going fast?
Yeah.
It's okay. I think. Yeah.
Okay, thank you then. Sure. Okay. So in SIMUFACT forming, you have different modules. So that is cold forming, hot forging, sheet metal and mechanical joining, pressure welding process, okay, rolling and ring rolling process, and open die forging and heat treatment also. So SIMUFACT on an underline, like in one line, when you ask about what SIMUFACT forming will be doing, so anything where there is a deformation involved, SIMUFACT will be able to simulate that one, and specifically metal, because we have another tool called DGMAT, which will take care of the composites, but SIMUFACT forming will currently take care only about the metal-based manufacturing methods. Okay, so in all these things, that what you see common is deformation. Okay, and here we can also do the heat treatment analysis in SIMUFACT. Now, where do we see the SIMUFACT? We can see the SIMUFACT in manufacturing process and in assembly line. So this MSc as a product has a completely different set of products altogether. Okay, as a company, MSc has a different set of products. So this can These can join, these can start from methods, and then it can go up to the system level analysis also. So among this particular product life cycle, SIMUFACT farming will be in these two stages, that is in the manufacturing division and in the assembly divisions. So where in the manufacturing domain, so SIMUFACT farming and SIMUFACT A2 will be there, and in assembly, SIMUFACT welding and joining will be there. Now, what is the main motive of developing this software? What is the philosophy behind this developing software? Is that shifting all the experimental tryouts into virtual tryout. Okay, so that means whenever we are doing any new development, so we tend to do many experiments. So the aim is to shift those experiments into virtual environment. I am not saying that we'll be removing the experiments. We will be shifting that physical experiments to a virtual environment. Okay, so that means you will be doing any type of process that you want to make it on the shop floor. You will be first simulating it, and then doing the virtual tryouts in the virtual platform like simulations. And then once we are satisfied, then we can go for one round check to exactly compare our results and see how much we are deviating. Okay. So this is the same philosophy for all the three products of SIMUFACT, like be it SIMUFACT farming, SIMUFACT welding, or SIMUFACT additive. Now, one great advantage coming to the SIMUFACT farming, and this is the advantage that we got it from the users, feedback that we got from the users, that is really user friendly. That means the type of input that SIMUFACT will be asking is exactly a particular operating parameter. Even though it is a FEA software, finite element analysis software, the FEA part has been tuned in the background for a what do you say, experimental users, so that people can concentrate on the experiment parameters rather than on the FEA parameters. The same thing can also be used for an advanced FEA person, because he can access the solver through subroutines and then try out his different variations. And now one more advantage here is a modular organization. So this modular organization helps us in fine tuning the process. Say, for example, in cold forming, so the general relationship with the stress and the strain data is like the stress is a function of temperature, strain only. So, but in the hot forging, it will be a function of strain rate, and temperature also. So, like this, based upon the type of application, the system, the development team has tuned the software such a way that it will be working really better for the particular process. Okay. And coming to the first module, there is hot forging module. So in this module, like first thing is the main aim of this module is, or the whole software is to replace the shop floor trials. So that's what. So when you want to replace the shop floor trials, or when you want to take out the experiments, the first thing it should do is it should mimic the process. Whatever is the process that is going there, it should be able to exactly create the same process in virtual environment. And followed by that, then it should be able to detect or identify any flaws during the process. That means in this particular hot forging analysis, you will be able to see what will be the pre-form shape or intermediate shape, so that you can use the software to do many trials and come to a optimum pre-form shape, which will be giving the final result, final product that we want. And also coming to the defects. So are there any folds or underfillings, which generally happens in hot forging scenario? So those things can also be identified beforehand. And apart from that, we can also look for like what is the material utilization, saying that because we know what is the initial raw material and we know how much is our final component. Like you can see, you can even do the trimming operations also here, like the video that is being shown here. The trimming operations can be done in this also. So that's how you will be able to calculate what is the final volume of final weight or volume of the component. And then we'll be able to get what is the yield also directly. So, I mean, this can be calculated easily, but we can say it is done through the software automated. Like you can do it directly through the software, like a streamlined process, and also higher output. So with this ability to look into this, what is happening in the tool, what is happening during the process, you can optimize it better, so that you will be able to get a better yield out of it. And better machine utilization is something like from this software, you will also be able to calculate what should be the external energy. That is, when you're talking about presses, so what is the energy that a press need to put? So what is the press force? Or if we are talking about the rollers, So we'll also be able to talk about what is torque needed. So those type of machine utilizations. So from this, you will be able to get that details also. So which will be really better in terms of like what should be the requirement, or can we perform this experiment or not. So those type of initial testings can be done quickly on this tool. And also product quality, like defect locations. You can see here, like this is the actual component which is being extruded. And you can see the predictions, how it has, SIMUFACT has predicted the similar wavy kind of behavior in the defects. So that's a whole thing on SIMUFACT forming. And coming to the next one, like in cold forging or cold forming process. So in this process, it's also something like you can do a proof of design. So that means that how many stages that you want to perform this operation, and how is the material flowing during each and every operation. You can see here the small yellow lines here. They are actually the material flow lines. So you can see during the process how this yellow lines gets deformed. So the deformation is nothing but how the material is flowing. Okay. And here also you will be able to find out what is the crack, if there are any cracks. So you can also detect those cracks. Okay. And also like you will be able to try to see like if there are any folds in this process, because even you go with a closed condition, so there might be chances of folds. So you can see that fold behavior also here. And also coming to the next one is like you can also have multi-stage. Like you can see here, the component is already pre-stressed because of the previous operation. So even though they are being done in separate operations, you can transfer the results from first operation to the second operation like that, and you can create a complete streamlined process. And also here you will also be able to calculate the tool life, because in cold condition generally there will be high stresses coming from the tool or a resistance. So because of that, the tool is something which we need to keep in mind, which is really important. So the tool life also can be analyzed here. Okay. So these are the things that which a cold forming mechanism will be concentrating on. And one really advantage or the unique thing that with SIMUFACT is you can have really multiple tool kinematics. So there is no compromising on the tool kinematics. We can address every detail. Like for example, there are some 4 tools moving in like 4 directions. Okay. And you want to see how they will be behaving. So yes, you can specify individual motion for individual tool, and they will work independently. Or if you want them to move with a certain correlation, like with the stiffness or the spring loaded systems, those things also can be simulated in SIMUFACT. And sheet metal forming, so which is like a really strong point when it comes to the looking at the thickness and the thinning and thickness profiles of the formed component, and also main important thing, the spring back calculations. So here you can see these are the rollers which are actually doing the operation of like deforming this particular gear disc carrier. So now in this operation you can see clearly like individual roller is at a different orientation and they have to rotate. So with SIMUFACT, we will be able to create that individual roller orientation also and view that individual kinematics also. So that's what I'm saying, like when it comes to the tool kinematics, SIMUFACT has no limitations on that. We are really good at giving the input as a tool kinematics. And next one is open die forging, so which is like ring rolling, or sorry, rolling, radial forging, ring rolling operations. So all these things comes under open die forging. So what is the advantage, or like what is the difference between open die forging and a hot forging is that the type of input that you specify to the system is like exactly like what you do it in the shop floor or in the experiments. So generally when any open die forging operation is being done, so it is done through a hydraulic press or like some kind of a hammer press where the motions are predefined. So with one set of inputs, so the press automatically takes care of those inputs and then starts doing the deformation. The same way here also, you can give one line input and it can deform the whole thing in a sequential way that we want. So that we'll also be able to tell what will be the stages or like what will be the dimension after the complete cogging operations. So like that. So this is a cogging operation and this is a tube sheet forming or radial forging, the other terms. So this is the shell forming, and you can see you can directly take the ingot as an input raw material, and then we can also calculate the analysis in terms of porosity closures. So those things also can be done here. And this is a ring rolling operation. So where this is the initial small ring, pierced ring, and then this is after final formed ring. So here in ring rolling operation, the guide rolls are generally taken care by the software. So software analyzes where is the ring and what is the ring diameter, and based on that it positions the guide roll, And the same way for the axial rolls also. As the ring diameter expands, the axial rolls keep moving outwards. So it will be directly taken care by the software. And software can also do the heat treatment operations, as I mentioned. So it can do quenching and tempering operations, case hardening, heating, cooling of the specific locations. So it can do a localized heating or a like complete global heating also. So in heat treatment, we generally try to calculate what is the hardness of the component after the heat treatment and what is the phase fractions after the analysis. So like that, we'll be able to calculate the different effects of the heat treatment, like for example, water quenching effects and air cooling effects. So all those type of experiments can be done with this heat treatment analysis. And also we can do the case carbonizing process. Okay, so where you can find like how is the carbon distribution, like how much is the potential of carbon on surface, how much is the potential of carbon on the core, what is the case depth. So all those type of analysis can be done through SIMUFACT heat treatment module. And next one is like mechanical joining. So even though it is a joining process, so instead of being in a SIMUFACT welding tool, it is actually in the SIMUFACT forming tool, because the mechanism of this mechanical joining is because of deformation. So whenever, as I mentioned, wherever there is a deformation involved, SIMUFACT forming will be able to simulate that process. The same thing here. So in this particular mechanical joining operations, there the rivets will be deformed and it will be deforming the sheets. So that's why it is being currently analyzed under SIMUFACT forming. So here you can optimize like what is the rivet geometry, die geometry, and if there are any modification that we need to do for the process parameters. So all those things we'll be able to analyze it beforehand. Okay, so this is a complete thing of SIMUFACT forming. So as you coming to your queries on like forming and rolling and cutting. So since each and every operation involves a deformation, SIMUFACT will be able to analyze those particular operations really better. Okay, and I'll just take through a couple of case studies on forming analysis, so that like we'll be able to see how SIMUFACT is being used in one of the case. Okay, this is a cold forming analysis, and so here this is the case study where they are making a fasteners that is like a bolt, nut and bolt operations. So now here it is a 3-stage process, forming process, and 1 stage cutting and 3 stages of forming. So the objective is to make these threads along with this particular washer kind of behavior, bulging behaviors. Okay, so now the first stage is to cut it from the rod. So you can also do this cutting operations. And so this particular like the specialty of this case is that, so this whole detailed view of the tool setup are also designed in SIMUFACT, like analyzed in SIMUFACT without even the process being available physically. So this is already a complete concept which they have designed individual tools, like even the ejector pins or like strict press fitting tools. So all those things can be set up in SIMUFACT, and they have analyzed this thing in that way. So as you can see, like first complete new design. So there is no machine available, there is no physical tool available before doing this operation. So now everything is a complete design. So now they are able to recreate the whole setup what they want in a virtual manner, and they have like went through the designing the complete process. So you can see here. Sorry.
Yes.
Sorry. Just a minute. Okay. Okay. So there is a question like how to make cold forming simulation boundary conditions. Okay. I'll explain that. I'll do that. Okay, so now as you can see here, this is okay. I'm not sure why I'm unable to play it, but okay, let me go here. So in this, what happens is like at every stage, you will be able to capture what is the stresses, and then you will be taking care into this particular multi-stage operation. So you can transfer the results from one stage to other stage. Okay, so with this, you will be able to capture each and every detail. So here, not only a particular planar motion, you can also create this wedge type of motion dice. So that means you can see here, the yellow color one is initially on the top, now it is at the bottom, because there is a deformation. So the wedge, so this green color one will be pushing it down, the wedge will be moving inward direction. So like this, you can create, as I mentioned, there is no problem with them tool kinematics. Okay, so we can really address the tool kinematics very well. Okay. Okay, now coming to the question of how can we set the boundary condition in cold forming. So then I'll directly go with a demo process. Okay, so that you will be able to see how I am setting up the process and every details. Okay, so is it okay? Okay, can anyone respond? Like, am I audible?
Yeah, I can hear you.
Sure, sure. How about the team? Our Jakarta team, like, are they able to hear me?
Pak Damura?
Yes.
Okay, okay, you are able to hear. So what I'll do is, to answer your question of how to set up the boundary condition, I'll quickly open the software and show the demo in the software directly. Okay.
Okay.
Okay. So now you can see the software. So this is actually the SIMUFACT forming software interface. Okay. Now here I'll just create a new project.
Yes. You can see your project.
Sure. Okay. 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 So I just need to give a name. Okay. Now here all these modules are there, so we can select the module. So like, since you are looking for cold forming, so I'll just click on the cold forming process and say okay. And it will ask us different types of process which we want to use. So if the process that which we want to simulate is not exactly coined, the name is not available here, we can go with the forming general. Okay. Now in this scenario, I'll just give a small example by using a upsetting process, simple upsetting process. Okay. And so you can analyze it in 3D, 2D, or 2D planar. So I'll go with 3D analysis. And number dice quantity, 2 dice, a top die, bottom die. So there are 2 dice. Okay. Now in SIMUFACT, this particular left window is called process tree, and this is called the inventory window, and this is the model view. So whenever you want, wherever you want to assign any component to the process tree, it should be first assigned in the inventory window, then only you will be able to assign it, like generally our general procedure. So it is the same rule. So now first, as a FEA, the first thing that we need is a domain. So for domain, here in our terms of FEA, it's a geometry. We take the geometry and discretize into different small elements. So that's a process. So here in geometry, we can take it through a different types of CAD tools. So you can see all these type of CAD interface can be imported into SIMUFACT. Okay. or we can use it as simple basic shapes also. Okay, cube, cuboid, cylinder, these are the basic shapes. So now for this example, I'll use a simple basic shape cylinder. It's a diameter of say 150 and height of 30 units. So which will be a cylinder that is nothing but our top die. So I'll say okay. Now you can see the name here came of cylinder, so I'll rename it top die, and I copy the same exactly because it will be the bottom die. And now coming to our workpiece, that is the component which will be deforming. So I'll use the same cylinder again, but with a different dimensions. So diameter of 75 and say height of 50, or like say 100 and height of 50. Say okay. Billet. Now we are done with our geometry. So we have created 3 geometries in our work, in our SIMUFACT inventory window. Now we need to assign these geometries to specific object here. Now SIMUFACT, we need to tell SIMUFACT which geometry is what. So now bottom die, it's simple drag and drop operation. Bottom die will be assigned to die 2, and top die will be assigned to die 1, and billet will be assigned to workpiece. That's it. So this is how you take the components into SIMUFACT. Now, since everything is having the same origin, they are not properly positioned. We'll position it later. Okay. Now we need to create a material also. So we have a library of materials. So from there we can take the one material out. Okay. And once we load the material, meanwhile I just explain it. Once we load the material, we need to define the presses. Presses are nothing but how the tools will be moving. This is exactly one way of mechanical boundary condition. The first thing is, when it comes to mechanical boundary condition, we specify the mechanical boundary condition through presses. So what type of kinematic motion it is having. So is it, if it is rigid, that is, it is not moving anywhere, then we will not assign any press. That means the system default takes it as non-moving component. That means it X, Y, Z for that particular component are fixed. But when you want to specify that what is the direction, if you want to let it go in one direction, then we can also specify what direction it is. So that is the next level of boundary conditions for a mechanical condition. Now, when there is other way, like when you want to forcefully move it, that is by a specific displacement condition, we can specify the displacement condition in our presses. And when it comes to the interaction parameter, that is mechanical interaction parameter between two components, that is being given by the friction. So this is a boundary condition between two components. Okay, that is being given by the friction. And the third one, thermal boundary condition, is being defined by the temperatures. So it defines what is the initial temperature of the component as a global entity. And also it defines what is the heat transfer coefficient from the component to the surroundings, a complete thermal boundary condition. So we take care of the mechanical and thermal boundary conditions through these 3 items. Presses will be giving us the mechanical boundary conditions. Frictions will be giving us mutual interactive boundary conditions or contact related boundary conditions. And temperature will give us the thermal related boundary conditions. Okay. Just a minute. I'll just add the material 1 minute. So I have added the material. So now this is the material which I'll be using it for our analysis. Okay. Now I'll define the presses. So presses are nothing but our mechanical boundary conditions. So I'll go to manual. So here we can type, we can do different type of mechanical like press motions. One is crank press, hammer, screw, hydraulic, or tabular motion. So the word press might be a little bit confusing, but actually this particular word is used to say the tool kinematics. How is the tool moving? So to inform or to give the information about that, so this press is being used. Okay. For example, if you have a cold forming press, a cold forming machine, even though it's a machine which is cold forming but not a press, but we'll be using this entity to determine or to define its motion. That's it. Okay. So here in tabular motion, you can have different motions with respect to directions also. So for all these other presses, there is only unidirection motion. They will be either moving in only one direction always, be it a hammer, hydraulic, or anything. But when you want to have multiple direction motion, like when you want a particular component want to move in certain angle and then rotate it again out like that, so then we go with this translation motion. So in this in this tabular motion, we can also specify if there is any spiral type of motion. So along with translation, the rotation also we can specify. So like this, we can clearly give the tool kinematics really very well. So it's not only time velocity or time versus stroke, that means displacement versus velocity or displacement versus force. So all those details can be specified if that particular motion is what we are looking for. So for this analysis, I just use a simple hydraulic press. So here this constant is a velocity. So the 10 mm per second is a constant velocity. That's the current boundary condition for the tool which I'm going to attach to the press. Say okay. Now you can see hydraulic came up. Now friction is a boundary conditions that we have, interaction boundary conditions. So we have library of friction material, like friction details. So since I'm using bulk cold, so we have different materials generally be used, and what is the different types of good, bad, or medium type of segregations, and we can modify the values if they are not as per as our requirement. Okay. So currently I'll use a medium friction cold, say import. So we can even alter the values here. So it is generally uses a Coulomb law or a Coulomb shear law. So based upon our requirement, we can alter it. So here you can have different models of friction here. So Coulomb law or shear law, Coulomb shear combined, or IFUM models. So based upon the type of analysis that you are doing, you will be choosing the different friction models. So here it's a cold and medium friction. So that's why the values are small. And now next one is temperature boundary condition, thermal boundary condition. So I need to have a thermal boundary condition for my die, which is a tool. And also I need to specifically separately mention the boundary condition for my workpiece also. So manual. So now it is initial temperature is at 30 degrees centigrade. And here we will be giving the boundary conditions in terms of heat transfer coefficients. Since it's a cold condition, then we will not be really worried, or we don't need to really take care of the heat transfer to the surroundings, because there will not be any major heat changes. But in hot condition, we just need to take care of these values. So it is like heat transfer coefficient to the environment, that is to the surroundings, and heat transfer coefficient to workpiece, whatever is the component, deformable component that we have added. So how does this heat transfer to the workpiece is interacted? So we can specify an automatic value which the developers has added some details into that. And also you can also specify a table based with respect to pressure, or table with respect to temperature also. So we have a degree of freedom to choose different types of approaches. Okay. And also you can also set the emissivity value, so based upon requirement. So these are the thermal boundary conditions which the system will be handling it. So this is the initial temperature, and these are the initial boundary conditions. So temperature has been defined for a tool. Now I need to define the same thing for my workpiece also. Manual. So it is also 30 degrees centigrade room temperature, and it has only one interaction parameter with the environment, because the interaction with the tool is already taken care in the tool parameters. Now the workpiece, it has only one interaction with the environment only. So whenever workpiece interacts with the tool boundary conditions will be applied. When workpiece is interacting with the environment boundary conditions will be applied. Okay. Say okay. Now we need to assign it to the process. So assigning the process is simply drag and drop. So first let us assign the thermal one. So temperature billet, temperature for my top die, bottom die, and the friction factor is given for the tools, so that whenever the tool gets in touch with the workpiece, this friction factor will be applied, because we just need to give it to anyone. That's it. So that's why we are specifying it to the tool. But interaction is between tool and workpiece. So it doesn't mean that there is no friction to workpiece. That means friction is not considered. No, it is not like that. Since we have specified the friction to the tool, so whenever the tool comes in contact with the workpiece, this friction law will be applied.
This questions if the temperature can change in depend on time.
Yes, temperature can change depend on time. Yes. So even though it is a cold forming process, the adiabatic heating, that is mechanical energy converting into heat, can also be simulated in this analysis. So let me run this analysis. Once the analysis is done, you can see that even though I gave my temperature as 30, you can see there will be a slight increase in the temperature in the core region, that is in the center of the workpiece. Okay, I'll show that once. So once we have assigned everything, now we need to assign our hydraulic, that is the thermal mechanical boundary condition. Mechanical boundary condition. I'm attaching the top die to the hydraulic press. That means that the top die is the one which is moving, bottom die is stationary. Okay. Now let me position the tools properly. So initial positioning is also important, that how the domain is arranged. So right click positioning. So currently the top die. So in SIMUFACT forming, we have different types of positioning methods: translation, rotation, gravity, and bounding box approach. So currently I'll use translation. So I'm just taking it up, like dragging, just hold and drag. That's it. There is no major things. Now I use gravity positioning, translation only. In gravity is in this direction, it will come and exactly sit here. Now I'll select this guy, translate it down first, and then I use the gravity option, translation, fit it. So it exactly goes and sits. So we are good now. So the positioning is correct. So all the things are satisfied, but one thing is left out, that is in finite element analysis, the first important factor is mesh, domain discretization. So now I just need to create this mesh for my workpiece. Since our tools are non-deformable, so we don't need to create mesh for them. We need to create mesh only for the deformable entities. But if you want to make the tools also deformable, so you can see right click, die type. So the different types of dies, that is deformable die, where the mechanical and thermal conditions are also activated for the tools also. This is rigid die without heat conduction, that is there is no thermal condition, heat change in the die, but the die temperature will be maintained, that is 30 degrees centigrade, but die will not increase its temperature. Okay, so die will act like a source or a sink based upon the temperature, relative temperature difference. Okay, if the die temperature is higher than the workpiece temperature, then it will act as a source. If the die temperature is lower than the workpiece temperature, it will act like a sink. Okay, so that is that rigid die without heat conduction. But there is the option of rigid die with heat conduction. So in this scenario, what happens is the die temperature also increases or decreases based upon the workpiece temperature. So if the workpiece is at a high temperature, then die will also increase its temperature because it is in contact with the workpiece. If the workpiece is at a low temperature, die will also decrease its temperature based upon the because of the contact. So this is the different types of dies we can choose. So in this analysis, I am using only rigid without heat conduction. That means it doesn't need to calculate any mechanical condition. It doesn't need to calculate any thermal condition change in the dies. Okay. So now, but for a billet or the workpiece, this is important factor. So now I am going to mesh. So in mesh, we have different types of meshes, that is tet, hex, and tet mesh, hex mesh, sheet and ring mesh. So when we are using a sheet metal, we use a sheet mesh. When we are using a hollow cylindrical component, we use a ring mesh. And other applications based upon the accuracy, we'll try different types of meshes. Let's go with hex mesh. So I'll leave the default values. So create initial mesh. And in SIMUFACT forming, during the analysis, if there is any requirement for remeshing, SIMUFACT triggers the remeshing by itself. Okay. So we don't need to worry about large deformation affecting our results quality. No need on that. No issue on that. Say okay. Say yes. So now you can see a remeshing parameter has come up. So this is a remeshing parameter. Now, once we are done, so we have set every boundary condition, how which one has to move. But now we need to specify the final condition, that is how much it has to move. We said that it has to move at a certain rate only, but now we need to specify that how much it has to move. So that is being done in our forming process, where we specify it as a stroke. So I want it to move by 20 mm. So that's why the stroke is 20 mm. And now I will just play the press animation to see whether my boundary conditions, the mechanical boundary conditions are set properly or not. That means tool kinematics. So the bottom die should not move. Top die should move at a certain rate up to 20 mm. So let's see this. So you can see the bottom die is not moving, top die is only moving. That means our boundary conditions are correct. So we are done with the process setup. So it hardly takes for any really experienced user. So it might be taking something around 5 to 10 minutes maximum to set up a model. Now we are done. Now only one thing, we just need to start analysis. So it says no material is defined for the workpiece. That means whenever there are any errors, so it will show the errors like this. So we didn't define the material to the workpiece. So we need to assign the material. So just drag and drop. And now let's start the analysis. So no issues. So you will just simply start the analysis. So now during the analysis, we'll see the effect of temperature change. Yes, it directly calculates the temperature change. And can you enter the temperature that can changes every time? Okay, so the analysis has started. Now I'll just cut through the section and we'll see it, what is happening. Okay, so deformation is started and deformation is going on. Okay, so this is a deformation happening. Now if I see the temperature change, so you see that there is a slight change in temperature. You can see that. Okay, but just for the querying points, so we'll just query the points at different locations. So I'll see the temperature here. You can see it's 53. You remember we gave 30 as our initial temperature, right? But now it is 53. That's because of the adiabatic heating. That is mechanical work converting into some amount of mechanical work is converting into thermal energy also. So that's what it is happening here. So reload. So now let me, if I see the previous scenario, it is at 77 at the final stage. Okay. And now if I go to the initial stage, so this is at 30 degrees. As we saw, at initial temperature is at 30 degrees. But as it goes, so you can see the temperature changing a little bit, 30.8, 33.54, 37. Okay. You can see the temperature increasing. So like this, the thermal effects also considered into the system during the runtime. So is it answers your question or is it something different?
Silakan Pak Damul.
Meshing model that is used uniformly or tightly in certain parts. Yes, currently I have given a default element size, but you can import the meshes from different mesh tools also. That feature is also available in the SIMUFACT, where you want to have really close tolerance. So those things you can have it through SIMUFACT also. That is possible. Is it answers your question or is it something else? Okay. So like in meshing types, we have two types like hex and tet. So these two are the meshing technology that we will be using. So tet mesh is like in hex mesh, there are two different separate categories. So one hex mesh, you can use it for generic for everyone. But when there is a sheet metal where you want to uniformly mesh it, So in that scenarios, we have a sheet mesh, which is also again a hex element, but the meshing methodology is different for that. That's why it is separately named out. And for a hollow cylinder object, so we have a ring mesh. It also gives a hex element. So it will be, but the meshing methodology, like the way it meshes, so that's a different scenario. That's why we have two different types of meshings other than hex mesh. But when you talk about element technology, we have two element technologies like hex and tet. So these two are the element technologies that SIMUFACT will be using. So when it comes to a solid element, when it comes to sheet metal applications, SIMUFACT will also have this solid shell element approach. So where it takes a solid element only, not a shell element, but it creates it different layers inside the shell element. It's a hex with a solid shell. And once we are done with this analysis, so we can also see what is the load requirement, like how much is the press tonnage. So those details you can find. You can see this is the press tonnage required in kilonewtons. At every stage, how is the press tonnage increasing? So we can able to see that details very well. And if you want to track certain point and you want to know how is the strain rate or strain being developed for a point, so we can even do that one. So just simply click on this and say this is the strain, plastic strain. Then I'm just clicking on the center point here and say plot. So this is the plot. So for this point, it plots the time history plot. That means with respect to time, how is the history of this point? So this is the current effective plastic strain for this point. Okay. If I want to see what is the temperature for this point, so this is how the temperature is raising for this point. And how is the strain rate? So this is a strain rate. And what is the stress at this region? Effective stress. This is a stress. So like this, we can select points, and then we can also do a quick analysis on those, how the points are moving with respect to time. So those analysis also can be done. Or we can also pick, say, a couple of points regularly. Can you show the mathematical model used in the simulation? Okay. We directly run it, but we don't have access to the source code right now. But I'll ask our development team to give details about the mathematical model for running the simulation. I'll get back to you on this particular point. So we don't have access to directly to source code, but we don't have information about that. So I'll just check with the development team and revert back to you on this particular question. What mathematical model is being used for forming analysis? Okay, so now just continuing my thing. So I can have a couple of points here, and I will do a quick plot. So in this plot, I can have a path plot. A path plot is nothing but with respect to this point, how is the value varying? So this is a point, and I can also use it as a displacement distance in terms of x coordinates. Let me take it as y coordinates. So how is the y coordinate? So as the y coordinates is increasing or decreasing, so you can see the graph, like how the variation in the strain rate, strain. And also you can do the same thing with the variation in the temperatures also for this time step. Okay, so based on that, you can choose how the different types of post-processing analysis that you can do. And also we can also even export the analysis here. So you can also save it as an image, or you can also export it, export the data in X and Y coordinate data. You can export it, and you can further analyze with any other different tools if needed. Okay. Any other questions?
No, no question. You can continue.
Okay. Fine. Now the same type of inputs or the same type of details we'll be giving it for the rolling application also. When it comes to a rolling process, we exactly specify our setup exactly like this. But instead of translation, what happens is for the hydraulic press, we'll be using a table press. That means where we have to define our rotation motion. So the angular RPM, angular velocity, is being given in the table press. So we define the table press based upon time, say up to 10 seconds, I want it to rotate with an RPM of say 30 RPM. So this is how we'll be specifying the boundary mechanical kinematics condition for a rolling application, and rest all procedures are same exactly as it is. Okay. Now meanwhile, I'll just open the small rolling project from our examples. So SIMUFACT forming, we have some predefined demos and example models. I'll take a rolling general, flat rolling process, and I'll just open this model. So here we can also even analyze the tool stresses also in our analysis. So as you can see, the rolling first pass, you can see the setup. So only difference is the rotation. So we'll be specifying the angular momentum, angular velocity for our tools. That's the only difference with respect to the cold forming or hot forging or the location where the dice will be moving in translation condition. But here the dice will be rotating in particular axis. That's the only difference here. And rest all the things are same. You can notice that the workpiece is having a mesh, geometry, the material, temperature, and the remeshing object also. Okay. Same way for the top rolls or the rollers or the tools, you have geometry, friction, and temperature. The same thing that we have it for our cold forming process also. Okay. Now let me show the results for this. So initial billet. And since we can specify the interaction parameter between each and every tool, so that's why we don't need to worry whether the tools are interfering with each other, because we specify the interaction, whether the tools there should be any interaction or not, we can specify those details. Okay, so that's why we don't need to worry on that, the contact related aspects. So you can see that like at every stage, so it's a 2D analysis. And these results can be taken to the next operations also if you want. Say for example, the geometry, in the previous scenario, I have created a geometry from a basic shape, right? Now, for example, the same process of our cold forming, you want to take this deformed geometry, okay, with results, everything. So we can just simply say geometry, right click and say from result. So from result, when you say it already has this upsetting FE3D process with billet and 100% result data, say okay. So you can see there is a slight change in color. That means it is having results in that. That means it's not only a uniform simple component, it is having a component data plus the results also. That means it is having every element is having its own strain, stress, temperature, and other details also in that. Okay. And we can use this geometry to the next stages, next further subsequent stages whenever we are analyzing it. Okay. So with this, like this is the rolling process. And so any questions on this rolling specifically?
No question.
Okay, so in the same rolling process, you can have a forward motion also and backward motion also. Very simple. We just need to modify the in the rotation parameter, instead of the next time steps, instead of having RPM plus, you will specify the negative RPM. The moment you specify the negative RPM, the rollers will be rotating in the backward direction. So it will take the workpiece along with the backward direction again. So those type of analysis will be able to perform with a simple thing. Okay, and so let me take one example on trimming operations. So in trimming, in SIMUFACT, we can do two different types of approach. One is shear based and other one is Boolean based. So the shear based operation is something like you will just simply trim it because of the deformation process. So you deform it and then you trim it. And Boolean operations are something like whenever you have a intersection, so that intersection region will be removed. So in this example, you can see it here. So you see there is the actual component is completely flat, but now you are only intersecting it with certain amount only, not completely through and through. So now when I say this Boolean operation, so it will just simply remove only the region where it is in contact or with intersection with that. That's a Boolean operation. When it comes to a directional Boolean operation, so you will see that wherever the direction is, whatever is the direction it is in, so it will remove the whole material in the direction. Okay. So this is the difference between a Boolean operation in the specific only Boolean and other one is directional trimming. Okay. And when it comes to a shear base, it's nothing but a deformation, then followed by trimming. Okay, like this, we can simulate the trimming process also in SIMUFACT. So just let me take this fine blanking operation. So you can see it here. Videos, yes. I'm just showing a small video on fine blanking operations. So you can see this is a fine blanking operation. The first initial stage is, see, you can see it deforms and then trims also. So this is a directional trimming, like shear based trimming, which we call it. So first one is deformation because of the tool. And then last stages, it will be trimming. So in SIMUFACT, we can specify this type of conditions really easy. So it's a, the whole ultimate aim is like it is being deformed. So that's why it will be trimmed at the last stages. So that's why SIMUFACT first deforms it and then trims it. Or if you don't want to have a deformation based trim, so if you're just looking for only Boolean operation trim, so that also can be done in SIMUFACT forming. Okay, any other queries?
And we can know the how much tonnage needs for this process, right?
Yes, we can note the tonnage that is needed for the process. And okay, since the tonnage point came up, for a rolling operation, we can also even find out what is the torque required for the machine or the motor to do that. So this is the axis press force. There is press force is nothing but the reaction forces onto the rollers. But all at exactly at the same time, you can also see the torque. What is the torque required to rotate the rollers in that particular direction? So what is the torque required to rotate the rollers in a direction? So initially, as the material is coming in, you can see the torque is increasing slowly. Once the material has completely entered into the rolls, the torque is almost like constant. And then once the material is coming out, it is decreasing. So even the torque and like torque requirements also can be calculated. And what is the roller force? Roller's reaction force. So that also can be calculated here. The same thing that we can do it for the cutting operations also. So during the cutting operation, so how can we, what is the force requirement? So those things also can be done.
Okay.
Okay. Any other queries or?
Silakan, any questions dari peserta?
Okay, what is the difference between 2D and 3D? Level of accuracy. So in 2D and 3D, only thing is like the model setup is exactly the same. There is no change. But accuracies, you can correlate the 3D values are much more accurate. That's very well known. 2D is close to 3D. Okay. So just to have a quick analysis view, let me rerun the same model of our cold forming with a 3D. We did it in 3D. Let me rerun it in 2D. So to set up a 2D, it's the same process. So what I'll do is I'll just simply copy without results. Okay, this is the second process, but it is actually 2D asymmetric because it's asymmetric process, and say okay. And there's nothing change I need to do. So it's exactly the same setup. I just need to define my 2D simulation plane. What is my axis which I am analyzing it? So 2D simulation plane is exactly workpiece center. Okay. And now I need to just simply mesh it. So I'll go with the quadri approach, 1.5, create initial mesh. Okay. So I have created a mesh and everything is done. I'll just simply run the analysis now. Okay, the analysis has started. So in 2D, 3D, there is really small change in the results values. You will not be seeing a major change. Just to have a quick comparison, we'll go with a side-by-side comparison. Let me take the model analysis for the first one. So as a quick way, we'll just see the graph plot. So this is the press force for the first one, and let's see the press force for the second one in a comparison view. So you can see the values. So they're almost close. As I mentioned, so there will be a variation, but they are almost close to each other. So this is how the graphs will look like. Just let me recolor it so that it will be clear. So the blue color is the process, is a data for the 3D. Okay. And the red color is the data for the 2D analysis. So you can see they are close together. There will be slight variations, I agree, but they are almost close to each other. Okay. Okay. So here there's a difference between 2D and 3D. There will be a slight change, but they will be almost close to each other. And when it comes to so that's the differences. So you can initially go with what is that a 2D analysis, and once we are done with the whole 2D, then we can go with the 3D one to have a really good close correlations in the 3D in terms of identifying the 3D defects also. So any other queries?
for future inquiry or questions, you can email to me or text to me, and I will convey to Mr. Sivasai.
Yes, that would be good. Okay. So any further questions, just or any other doubts which you feel like, okay, you want to do it once again and you want to have some more queries, some more explanation, just write it to Impress, so then I'll be able to receive it from him. So I hope like I have covered what you are looking for. So, and if any queries, just let us know. So we'll be able to come back and give an explanation on that.
Silakan Pak Damora, barangkali ada pertanyaan lebih lanjut.
No question. You can continue to presentation.
Okay. Like this is this is my presentation. So which I want to cover the basic things which you are looking for on the forming, rolling, and then on trimming operations, that is cutting operations. So this is what I have like set it for presenting it to your team.
Barangkali ada topik yang masih akan ditanyakan.
Maybe enough.
Okay.
One topic from
Milling.
Armansah to explain tuning.
Yes. So in SIMUFACT, the machining process, we have cutting but we don't have the machining process like milling and turning in the SIMUFACT simulations. So it's actually in development approach. Now I think it may take in the mid-year release, it might be coming. So that means like 6 more months it will be taking to come out. So but we have this milling and turning process as a part of a SIMUFACT additive process, where they'll be using it for a machining analysis, but not in terms of actual material removal, but in terms of the support removal in SIMUFACT additive. But for the forming, this milling and turning process is not yet introduced into the forming. It will be taking something around like 6 to 7 months to come out into the production also. So currently, we don't have anything related to milling and turning in SIMUFACT forming.
How about in MSc Mark, Mr. Sinipas?
Yes, exactly. Yes. MSc Mark, it will be that. That's the reason why MSc Mark is having. So now they're trying to bring that similar methodologies or the similar technologies into SIMUFACT also. So that's why I'm saying that it will take something around 6 to 7 months to come into the SIMUFACT product software directly.
Oke, jadi Pak Damora, ada namanya MSc Mark, itu adalah general purpose untuk manufacturing process simulation, dan milling sama turning ada capability di sana, tetapi lebih apa ya, graphic user interface-nya itu lebih mudah ada di SIMUFACT. Jadi mungkin sedikit lebih kompleks untuk menyiapkan modelnya di dalam Mark, tetapi itu bisa dilakukan.
Okay.
Since I don't have any details on milling and turning, that's the reason why I didn't explain any details on that. Where we can do the other process like cutting, forming, rolling. So that's why I focused on those details. Milling and turning, currently we can't do it in SIMUFACT forming now. But yes, there are plans for it to include into the SIMUFACT forming also in the next releases. Because some other tools of SIMUFACT are using machining now. So that's why it will be incorporated. but not currently. It doesn't have that facility now in the current version. So if there aren't any queries, then like we'll take it to the next levels. So if you have any other queries that you feel like after discussing with your team once again, if you say that, okay, we have some more queries, then just please write it to us. We'll try to address them as soon as possible. Thank you. Thank you very much.
Baik, Pak Damora, barangkali silakan untuk kita tutup acara kita hari ini.
Yeah, okay, baik. Thank you very much for presentation, Mr. Sifasai. Thank you very much for presentation. Terima kasih banyak sudah presentasi menjelaskan dari software ini, aplikasinya, karena tools software ini juga bisa kami gunakan ya nanti untuk di bidang mechanical engineering untuk proses manufacturing di proses pembuatan. Ya, karena waktunya sudah jam 11 dan sudah cukup banyak informasi yang bisa diperoleh. Saya ucapkan thank you very much. Terima kasih banyak partisipan yang sudah hadir di virtual Zoom ini. Saya ucapkan terima kasih. Selamat siang. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Sifasai.
Thank you. Thank you.
Goodbye.